So now we're going to talk about how you actually design the reaction that you're using in a redox titration. So we left off with this idea that I want to know the concentration of this platinum 2 chloride solution. And because that's not acid or base, really, I'm going to need to use redox chemistry. So when we decide that we want to do some redox chemistry for a titration, we have to think about, well, can this thing be oxidized or reduced? And what we want to do is kind of think about what atoms am I dealing with and what are the tendencies of those. And we can kind of break that apart based on where it is on the periodic table. So the first thing we want to think about is, am I dealing with a transition metal? The transition metals tend to all form cations when you ionize them, and they can form cations with different charges. We call them variable charged metals. And so if you have, say, something like copper, you'll see I've looked up, this is basically just reference information of all the transition metals. And I can see that copper can form either copper plus or copper 2 plus. Both of those cations can exist of copper. And that means that it is possible to reduce or oxidize either of those, right? You can oxidize Cu plus into Cu2 plus, and you can reduce Cu2 plus into Cu plus. So whenever you are dealing with a transition metal, you always, for the most part, have the possibility to do either reduction or oxidation based on what ion you have in your particular compound. For something like molybdenum, which is MO, there are a ton of options, right? Molybdenum forms a lot of potential cations, plus 2, plus 3, plus 4, plus 5, plus 6, and you can reduce or oxidize between them. These options are called the oxidation states. It's a reference to the oxidation number that that metal atom has in those particular ions. And so you'll see that for kind of the middle of the transition metal block here, there is a lot of possible oxidation states, but even most of these atom types, most of these transition metals, can at least oxidize between two possibilities. If you look at some of them, for example, yttrium, Y, only Y3 plus exists. So functionally in solution, you're only going to get Y3 plus, but you still have the possibility to reduce to Y. You can always go to like the elemental metal, where you could go to have a 0 charge. And so you can always do that. So when we're looking at, can I do redox chemistry for like a titration? If you're dealing with a transition metal, you can always change what sort of cation is present in solution. If you're dealing with the P block of the periodic table, so the right side past the transition metals, you're more looking at it creating different types of oxyanions or the polyatomics. So for example, chlorine, in terms of atomic ions, you're always just going to get chloride, which has the -1 charge. But chlorine can also form a variety of oxyanions, those polyatomics, that feature oxygen atoms in different numbers of oxygen atoms. So hypochlorite, chlorite, chlorate, and perchlorate. And we can see that in each of those, the chlorine atom has a different oxidation number. And so if you are dealing with a solution that contains chlorine atoms, chlorine ions, you can oxidize or reduce those depending on what sort of ion is currently present. So if you have, ClO2 minus, you can either oxidize or reduce that depending on if you want to, how you want to go or what is easier or more available. But you can always change basically the number of oxygens that are in those ions. Oxidizing is adding more oxygens. Reducing is decreasing the number of oxygens. And so you always have that flexibility. Chlorine is kind of the case where you have tons of options. Something like phosphorus, you can still form, say, phosphide, and you can form phosphite and phosphate. There is no PO2 polyatomic ion, but it's instead just PO3 3 minus or PO4 3 minus. So there is still some flexibility, but not infinite flexibility when it comes to forming these. And so there are all of these possibilities when it comes to even, say, the metals in the P block. For example, lead. Metals in the P block, or even some of the transition metals, can also still form oxyanions too, where you get, say, this PbO3 2 minus called plumbate. which has a different oxidation number than an atomic lead cation. And so you can form these, and so you have all of these possibilities. That's not to say that you need to memorize all of these possibilities. You just need to recognize that when you are dealing with redox, if you want to do a redox titration, you want to predict what sort of redox chemistry can I do, you want to look up, well, what type of atom am I dealing with, and what can I turn that into? What sort of possibilities can I get? And so, so those are the kind of things we want to be recognizing, the kind of things we want to be looking for. And what we want to do. Looking up reference information, not memorizing all this stuff, just being able to look up or understand and predict, say, how these oxidation numbers are changing. Is it oxidation? Is it reduction? If you're not dealing with elements, if you just have, say, molecules involved, they can still do reactions, redox reactions. There's a lot of redox reactions that are just molecules reacting. You can see some of the ions that we saw on the previous page, or just non-ionic molecules. And so this is bleach, ClO minus hypochlorite is the active ingredient in bleach. Hydrogen peroxide is another compound that also can do bleaching. And that's a redox reaction. When you bleach clothing, you're doing redox chemistry. So if you have a solution of ClO minus, that can do some redox chemistry. If you have a solution of hydrogen peroxide, that can do redox chemistry. And so those are possibilities of things that you can do and things that you can always have. So, it's more a matter of not necessarily memorizing all the possible redox reactions, because that's not useful. What's more important is being able to recognize, hey, I have this molecule. I should look up, can it do redox? If it's a transition metal, what sort of oxidation states are possible? If it's in the main group, those non-metals or p block metal, does it have, what sort of oxyanions can I form? What sort of chemistry can this tend to do? And interpreting that reference information, reading this and being able to say, is this a reduction half reaction or is it an oxidation half reaction? And therefore, what else do I need? So once you know what you want to do, say, I want to oxidize something, right? The possible chemistry is I want to oxidize or I want to reduce my analyte. That's when you pick your titrant. That's when you pick what are you going to put in the burette. And basically what we use is we use either really strong oxidizing agents or really strong reducing agents. And this is similar to the prospect of using strong acids or bases. Remember, we wanted to push all the way to product favorite equilibrium. We want to basically use a sledgehammer when it comes to driving this chemistry. So if you decide the thing that you're going to analyze in the titration needs to be oxidized, you use an oxidizing agent, right? And we've seen that oxidizing agent can characterize an individual reaction, or an individual reactants in individual reaction, but we also just use this language for permanganate and cerium-4. These are ions that really want to reduce. They really want to gain electrons, so they will oxidize basically anything you mix them with. So we would functionally, you need to make it a salt, right? You can't, permanganate is the active ion, but you got to make it with a salt. So you put it with, say, potassium, which is inactive, or with cerium-4. That's what you want. It's just the cation, but you got to put it with, say, sulfate. So cerium-4 sulfate is really common. For our reducing agents, iodide and thiosulfate are really strong reducing agents. These things really want to lose electrons. And so they're really good at giving electrons to whatever you decide to reduce. And so when you decide, hey, the chemistry I want to do in my titration is I'm going to oxidize something, you basically just look, okay, functionally you use permanganate because cerium's bad for you. So permanganate's pretty bad too. But I'm just going to use permanganate. We're going to run with that because that is the oxidizing agent to use. In much the same way that with your strong acid, you just used HCl. You didn't overthink it. You didn't get cute. You didn't use some weak acid. You just throw the kitchen sink at it, grab your HCl. KMNO4 is the same equivalent for looking up an oxidizing agent. Just use the strongest thing you have. Participation 4.3, question 1. You are going to use titration to determine the concentration of an FeCl2 solution using KMNO4 to oxidize the Fe2+ to Fe3+. What is the overall balanced equation for the reaction that will occur in this titration? Got your half reactions, Fe2+ to Fe3+,
and MnO4 minus to Mn2 plus. This is the first question on participation 4.3, due Friday, April 3rd, 11:59 p.m. over on Blackboard. The link to the assignment is linked below the link to the document with these videos. Again, you're going to use titration to determine the concentration of an FeCl2 solution using KMnO4 to oxidize the Fe2 plus to Fe3 plus. What is the overall balanced equation for the reaction that will occur in this titration? It's iron 2 becomes iron 3, and then permanganate becomes manganese 2.
All right, so if we look at our example, we were trying to figure out the concentration of our platinum 2 chloride solution. Okay, so we know that this is platinum 2, right? There's a 2 plus in there. If you look up the possible oxidation states of platinum, it's 2 plus and 4 plus. So we currently have 2 plus. Let's change it to 4 plus. Okay, so 2 plus to 4 plus, we are increasing the charge. That's an increase in the oxidation number. It's loss of electrons, right? It's becoming more positive, which means we are going to oxidize this. So in our reaction, we're going to oxidize it, which means we want the best oxidizing agent. That's KMnO4. So it's one of those things that just like when you decide, hey, I'm going to do HCl, I need an acid, you just use HCl. Once you decide I'm going to use an oxidizing agent, KMnO4 is the oxidizing agent to use. You don't need to think about it. Don't need to get cute. KMnO4 is kind of your standard good oxidizing agent that's not too unsafe, and you're ready to roll.
Okay, we had a participation question. Participation 4.3 was in this video. You got to answer it. And then we'll move on to the next video. I'll see you there.